The solids and crystalline solids. So this window over here is called glass, and it has no order. It's all kind of stuck together there. And here's a nice special piece of crystalline silicon dioxide, and you see it's nicely ordered. And quartz crystal, if you stress it, it develops an electrical charge, so we say it's piezoelectric. It also has different optical properties than amorphous glass. So as that last slide showed, amorphous solids lack regular three-dimensional arrangement of atoms, and glass is more than just silicon dioxide. Most glass has some of these other compounds in it. Soda lime glass is pretty common. That's probably what soda bottles are made out of. Now they're made out of plastic, but you can probably still find some glass ones. 3/4 silicon dioxide. There's the soda added, sodium anyway. Sodium oxide, some calcium oxide. Pyrex, my favorite. That's what all of our labware is. Pyrex glass. Why is Pyrex glass so neat? Low thermal expansion. You know, when I was a kid, we didn't have the internet or phones, and so what we'd do is pull out Mom's frying pan and put our marbles in there, heat it up, and then put them in glass and in water, and they'd crack and look all cool. I don't know if kids do things like that today. Yeah, so a marble's this soda lime glass, and it has lots of thermal expansion. So you heat it up, it's all expanded, and you put it in the cold water, and the surface of the marble tries to shrink, and it makes cracks. And so your Pyrex glass, cookware and laboratory glassware. One of the last parts of chapter 12 is on crystalline solids. So we saw the quartz had a very regular reoccurring pattern. The crystalline solid is going to possess a rigid long-range order. Its atoms, molecules, or ions occupy specific positions. So this thing here is called a unit cell. And you can see it represents one piece of this larger crystal. This thing just repeats farther and farther. So a unit cell is the basic repeating unit of a crystalline solid. There are 7 types of unit cells. I only ask that you recognize 2 different types. Simple cubic, which sodium chloride might be, but geologists and inorganic chemists, they go on and study this out in great detail. The difference between tetragonal, orthorhombic, rhombohedral, monoclinic, triclinic, and hexagonal. So the only ones I might hold you responsible for is simple cubic and hexagonal. So sodium chloride here. So out of that hexagonal class, there's this thing called hexagonal closed packed structure. So this is what I recognize when I go to the supermarket. And I go to the produce department, they got oranges stacked up, apples stacked up, grapes. And this is how those fruits stack up. Now if we look at just one layer here, I see kind of like that hexagon right here. There is the hexagon. And then when you put a new layer on, each new fruit goes into a hole, and so it's slightly shifted. And then when you start a third layer, it should be back to the original one. And if you ever tried to pack fruit away in a box, this is the best way you can do it. Properties of solutions. In chapter 12, we saw that like dissolved like, and there was interaction between the solvent and the solute. What is the solute? The solute is what gets dissolved. And here's one of these cubic crystals. So sodium chloride makes a cubic structure. Packed fruit is a hexagonal closed packed system. So the solution process, what does that mean? That means you have to get solvent, typically a liquid, And solute could be a liquid, or could be anything really. And you form this solution. And technically we say a solution is formed when one substance disperses uniformly through another. So this should be a review. Solutions are homogeneous mixtures of two or more substances, and the solvent is normally the component present in the greatest amount. Other components are called solutes. So a good example of a liquid solute would be ethanol, like in beer, maybe 6% alcohol, and the rest is what, for the most part?
Water.
Yeah, water. Now there's a product with the brand name Everclear, and that's like 95% ethanol and 5% water. In that case, what is the solute in Everclear?
The water.
Yeah, the water. So there's a good example. So we've seen a picture like this before. So this is the solution process. Here's some solvent. Here's a crystal of sodium chloride, and these water molecules have to get up next to the surface, and we see the positive ends of water grabbing onto a chloride, which is negatively charged. We see the negative side of water, the oxygen, grabbing hold of the sodium cations. So we got to break the interactions of the solvent, water being hydrogen bonded to itself, and then it interacts with the solute, and we call that solvation, the interaction between solute and solvent, solvation. And water is a pretty universal solvent, and when we're dealing with water, we can call that also hydration. So over here we have a hydrated chloride, hydrated sodium ion, hydrated chloride ion. We say the ions are hydrated in solution, or they're solvated with the solvent. The intermolecular forces between the solute and the solvent particles must be strong enough to compete with those between solute particles and those between the solvent particles. So you're all up to speed on intermolecular forces. They all play a role in the solution process. How do we express concentration? If we have a solute in solution, it can be concentrated or less concentrated. So we like to supply some numbers and actually know. So I mentioned beer, 6%. What does that mean? 6% beer. That means there's like 6 grams of ethanol in a total 6 grams of beer. This would be mass percent. And I tell my quantitative analysis students that when you're given a percent, if it's not specified what type it is, it's mass percent.
Solin means solution, correct?
Pardon?
SOLN.
Yeah, that's abbreviation for solution. So I don't know how many of you are familiar with Colorado, but when you're 18 in Colorado, you can go to a convenience store and you can buy beer. What kind of beer can you buy? Good, you're all young and not into that, so you don't know. They would sell 3.2% beer, and it was by volume, and it would say by volume right on the label. What? Utah's the same way? Alright, so what is this parts per million? Well, before we mention parts per million, what does percent mean?
Out of 100.
It means parts per 100. So a percent and parts per million, parts per billion, parts per trillion really has to do with what number you multiply to make some fraction, maybe like a whole number.
So would you use parts per million when you're dealing with like a smaller quantity?
Absolutely. Yeah, we don't like to say 0.000% or whatever. That gets tedious, and you can make an error. So, like, yeah, if you had 6 grams of alcohol and 100 grams of beer, and you put that on your calculator, that'd be a fraction of 0.06. And then we multiply it by 100, and we get 6. And we say 6%. And the little percent sign means per 100, or that this was done. So if we want to get back to the fraction, we divide by 100 and get 0.06. So parts per million, the same thing. Notice it looks the same. Mass, component, in solution, and total mass of solution times 1,000,000. So possibly last spring you did the gas chapter and Dalton's law of partial pressures and a few other things. Use this mole fraction. If you knew the mole fraction of a gas in a mixture, you also knew its partial pressure. So what is a mole fraction? Moles of component over the total moles of all components. That's the mole fraction. And this one you know like the back of your hand, right? Molarity. Oh, good. A few smiles. Molarity. Moles per liter. Moles of the component over liters of solution. Alright, well, let's pack your brain with some more similar but different concepts. Molality. And at this point in time, I got to be real careful and think about my enunciation and what I want to be talking about so I don't mix them all together. Very, very similar, you know, just an R substituted for an L there. Molarity. Moles of component per liters of solution. Molality. Still moles of your solute or compound of interest, but now it's in kilograms of solvent. Kilograms of solvent. And some interesting things I tell quant students, if you have very dilute solutions and a liter of water is 1,000 grams, that's a kilogram. So molarity and molality for very dilute solutions almost come the same numerical value. But once we get a little more concentrated, they can be very markedly different. And notice it's not kilograms of solution, it's kilograms of solvent. And that's really kind of convenient. Makes a lot of calculations a whole lot easier. But you want to keep that in mind, because I see students put the mass of the whole business just like you might be doing these others down there. Want to keep that straight. Colligative properties. What are those? Changes in colligative properties depend only on the number of solute particles present, not the identity of the solute. And we're going to look about at 3 or 4 of these. So when there's ice on your sidewalk, why do you put the salt on it? Yeah, to melt it. And you break up the hydrogen bonding by making the water undergo dipole ion interaction. Who's made homemade ice cream? And what do you do? How do you do that? Yeah, ice and salt. And so there's a variety of ways to think about it. You can think 6 kilojoules per mole when solid ice goes to liquid and you suck that heat out of the surroundings when you melt the ice. Or you might think you lower the melting point of the mixture to some below 0 degrees Celsius freezing point. So the first colligative property is freezing point depression, and we get a decrease in freezing point we call delta T sub F, and it's directly proportional to the molality of the solute. So we distinguish between molarity and molality by giving molarity an uppercase M and molality a lowercase m. So if we know the concentration of the solute, with our new concept here called molality, moles of solute per kilogram of solvent, and K sub S is a constant, and it's different for different solvents. So here for water, it's 0.51 degrees per molal. So I look at this like I look at everything. You forget this equation, don't know what to do, look at these units and it might tell you what to do. If I times molality times this thing that has degrees per molal. The molal cancels out, and I'm left with degrees, and that degrees represents a change in freezing point. So K sub F is the molal freezing point depression constant. Excuse me, I was looking at the boiling point. Here's the freezing point. We'll see that they're very similar. It's 1.86 degrees per molal. So if you know your molality of the salt solution, you can tell me at what temperature it would freeze at. And here we see boiling point elevation. So sometimes I ask students, you go home and you're going to make pasta and you throw some salt in the water and bring it to boil. Why do you throw the salt in there? I always get some students say, to make it boil quicker. And then I'm like, is this a kinetics issue? And then they say, oh no, to make it boil hotter. And then I say, if we actually put enough salt in there to make it boil at a higher temperature, it might make the pasta unpalatable. So once again, how much the boiling point is elevated is dependent upon the molality of the solvent. And once we have a delta T, we want to add that to the normal boiling point. And just as over here I didn't say, but normally water freezes at 0 degrees Celsius. If we have a 1 molal solution of sugar, we would go 1 times 1.86, and we'd get 1.86 for our delta F, and then we'd subtract that from 0, and our 1 molal sugar solution would freeze at negative 1.86. And you see here some other solvents, not this week, but in a week. We will use freezing point depression to calculate a molar mass in lab. We'll take a pure solvent, cool it down, and see where it freezes. Then you're going to add a solute, freeze it again, it freezes at a lower temperature. Then you'll have a change in temperature. You divide by the constant and you'll get a molality. So let's explain the change in boiling point. Freezing point, I just said it, breaks up the intermolecular forces holding the solvent together as a solid. But here's another colligative property, lowering of the vapor pressure. And you might say, oh, you don't need to explain it. Vapor pressure and boiling point are inversely proportional to each other. The higher the vapor pressure, the lower the boiling point. The higher the boiling point, the lower the vapor pressure. Raoult's law, a non-volatile solute. We could do sugar or table salt. They're fairly non-volatile. It says these solutes reduce the ability of surface solvent molecules to escape the liquid. So here's a liquid, and it has some kinetic energy, and some molecules escape. That gives you the vapor pressure. All right, then we dump in some sugar, and now we see a fat sugar molecule there, and another one there, and another one there. All right, so this random movement runs into a sugar molecule and bounces back down. So that slows down the rate of evaporation, and that affects this equilibrium. And now we say vapor pressure is lower, and our definition of boiling is when vapor pressure equals atmospheric. So you can see here, if you got something like this going on, you got to heat it up a little hotter. And here we see Raoult's law in one of these forms of concentration, the mole fraction. So here we have vapor pressure of the solution is equal to the mole fraction of the solution times its normal vapor pressure. Yeah, it's like in lab, you had a temperature of water and you went and looked it up, and it's like probably 18 torr. You dump some sugar in there, mix it up, you'd figure out the mole fraction of your water, and it's less than 1 once you make a solution, and that's going to lower the vapor pressure of water.